Okay, so we are looking at turbulent flow in the pipe. That's what you just did, in fact, right? We calculated V average divided by, or rather V max, which is what is in the numerator, V average. V average by V max is equal to 1 divided by 1 plus 1.3 square root of f. Okay, so if you haven't gotten it, just go back and try and do it. Okay, I just wanted to know whether you have done your homework or not. So what is that? Yeah, so V average by V max is this for the turbulent flow. So the difference is that, so we talked about this yesterday, V average by V max is half for laminar flow, and this is the factor that comes out for turbulent flow. So let's see what this means. Okay, typically, let's say if I take a Reynolds number of 10 raised to 4, then V by V max comes out to be 0.8. If I take Reynolds number as 10 raised to 8, then V by V max comes out to be 0.9. Okay, just some numbers. So given Reynolds number, you know how to calculate friction factor. We derived the expressions for that. So if you use that friction factor and substitute, this is what you get. Okay, so what does it mean? As Reynolds number get larger and larger, V by V, this average velocity divided by the maximum velocity becomes closer and closer to 1. Okay, when can average velocity become very close to the maximum velocity? When the profile is very flat. Okay, when the profile is parabolic, you had that factor as 2. Now this says that the average velocity is very close to maximum velocity. That means if you look at the velocity profile is going to be almost flat. Something like that. Okay. So that's what the velocity profile going to look like. So that's the information that you have really gotten. And in some sense, now this should start making sense to you, because turbulence flow, okay, or turbulent flow is full of fluctuating velocities. There are extra mechanisms for momentum transfer. So the gradients are not maintained that well. Okay, the gradients get actually smoothened out very fast. Okay, that's why you're getting this flat profile for the turbulent flow. Is that clear? Doubts? Okay. So what we are going to look at maybe next 10 minutes is effect of rough walls. So when I say roughness, okay, so let's say you take any material, let's say even if it's PVC pipe or iron pipe, the finishing, okay, that typically looks very smooth, but when do we call it smooth? When do we call it rough? Okay, when you look at it, you may not see that it has got any roughness at all. It may be like very small, but if you actually put it under a microscope, you will see that it's not really flat. It has got some troughs and some uneven area, right, that you would definitely see. So what happens is that even though it's such a small scale, it starts affecting the flow field. It does not affect a laminar flow, but it can affect turbulent flow. We'll see why it affects turbulent flow. So rough walls does not affect laminar flow, affects turbulent flow. Okay, so to see that, we need to go back and check our viscous sublayer or the wall layer. Remember, we said there are, if you look at the turbulent flow near a wall, we divided it for into three parts, right? There was a layer very close to the wall where the viscous stresses are much larger than the turbulent stresses, right? So that's what we call the wall layer. And we drew a velocity profile, and we said up to what extent the viscous sublayer or the wall layer is, right? Does anybody remember the number? Up to what distance would you see the wall layer? Check your notes. Five. What is 5? Y plus. Okay, when y plus is 5, up to 5, so from 0 to 5, you are expected to see the viscous wall layer. Okay, so let's say y plus is equal to 5. So from 0 to 5 is the viscous wall layer. So let's say y plus maximum, okay, is 5 that you are supposed to get. So let's write it as y. How is y plus defined? What was it non-dimensionalized with respect to? Is y max, okay, is 5, or y max divided by, let's say, d, where d is now the diameter of the pipe, is simply 5 u star divided by nu, right? Is equal to 5. Sorry, I made a mistake. No, this is y divided by, there's a d here, right? So I'm just dividing d on both sides, because I'm trying to, what I'm going to calculate now is the thickness of the wall layer compared to the diameter of the pipe. So I'm looking for a fraction which is y max divided by the diameter of the pipe. Yeah. No. So u plus is equal to y plus. So now y plus is up to 5 is when you have the viscous layer. It's just that we drew it on a logarithmic axis. So the value is still 5. Yeah, it's not log y plus. What is that? Oh, is it the other way? Okay, let's do that. Y u star by nu. Now is it correct? So therefore I should change this. Nu by u star is equal to 5 nu divided by the u star there. Okay. I want to bring in an average velocity because I want to write it down in terms of Reynolds number. Star. Let's say we define a u average d, and I'll put a u average upstairs also, so that I can write it as 5 times nu divided by d u average, which will become Reynolds number, times u average divided by u star is equal to 5 times 1 by Reynolds number times u average by u star. We wrote down an expression for u average by u star yesterday. What is that? Not u max, okay, not the one that you calculated now, u average by u star. In terms of friction factor, you would have it in your notes. Root of f by 8 or 8 by f? 8 by f. Root of 8 by f. Okay. phi max by d. Okay, so this is what the thickness of the wall layer is going to be compared to, let's say, the diameter of the pipe. Let's say you take a pipe of 10 centimeter diameter, and let's assume that Reynolds number that I have is 10 raised to 5. Okay, so if Reynolds number of 10 raised to 5 can give you a friction factor 0.018, and therefore you must be able to substitute and calculate what is Ym. Okay, so Ym by d comes out to be 0.001. So what am I trying to do? I'm just trying to estimate how big the wall layer is going to be, okay, in terms of some real numbers. So I'm just giving some numbers and trying to see how big it is going to be for a Reynolds number of 10 raised to 5. And I find that the height maximum compared to the diameter is going to be 0.001. So that would mean that if I have a 10 centimeter pipe, if D is 10 centimeter, Ym is going to be 0.01 centimeter. Okay, what is that? 0.1 millimeter. Okay, so if I take a pipe, let's say 10 centimeter diameter, okay, the thickness of the wall layer is going to be very tiny, okay, less than a millimeter, very close to the surface of the pipe. Okay, so that's the number that comes out to be. So it's really thin. One thing is that, remember, yesterday when we did the calculation, we threw away all that thing that was coming from the wall layer, and the overlap layer did, the logarithmic load did very well. One reason is this, that the contribution that's going to come from is extremely small. Second is that the thickness is so small that so if you go to that scale, okay, if you start zooming into the thickness of that wall layer, would you see the roughness or not? You would definitely see it, right? In other words, if you look at the wall layer is not really on a flat plate. It's actually seeing all the crusts and troughs, and it's actually moving on a very uneven surface. Agreed? Okay, because the thickness itself is very small. So that means, and then if there is a flow that's happening on a very rough surface, that flow is going to get affected by the roughness. That flow is not going to be smooth. Actually, another way of saying it is that wall layer itself gets disrupted because of the roughness. The roughness that you might not have imagined would play a role actually will destroy your wall layer and will affect the entire flow field. Okay, therefore, pipe roughness affects turbulent flow. That's the takeaway point. Is that clear? Yeah, so because it affects the wall layer, the other layer is on this layer. Because of the continuity, yeah. So for example, you need to maintain some stress balance that will get disrupted. So the entire thing will get disrupted. In fact, the log layer will remain as a log, but the arguments and the constant, everything will get changed. Therefore, the friction factor expression that you have gotten should be relooked at in the context of a rough pipe. Yeah. So for the laminar flow, it's basically going all the way there, right? So the layer is, there is nothing like a wall layer that is confined to the wall. There may be a small region where the roughness could affect it, but basically the viscous action will immediately smoothen it out because it's spanning all the way up to the radius. So that's why it does not get affected.